Okay, so I think we're back here. Welcome, hello. The next question is going to be number of islands. Given a 2D grid map of ones and zeros, one's land, zeros water, count the number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. You may assume all four edges of the grid are all surrounded by water. So this is kind of a classic question. There's a few ways to approach this problem. I believe, if I remember the different ways to do it, one way is to you can use a flood algorithm. So you can, what do they call it? It's called flood or paint fill algorithm. You can use a fill algorithm. You can visit every one approach is to visit every point, right? One by one, each index in the array, and use a flood fill algorithm when you see ones to fill them with x's. Once you see a 1, increment your counter, fill with x's, and then continue your check through each point in the through the grid, and obviously skip over zeros and x's, and that should work. You can use recursive flood fill. I think we'll implement that right now and see how that goes. So you do flood fill. Looks like the following. It's recursive. We want the grid. We're going to say we actually don't need. Oh, we use indices too. I and j. We also want balance check. We could say also is routine. Kind of an inline routine we could put in here too. We probably want, yeah, okay. We'll do int, we'll say rows, or we'll say columns. Yeah, rows. It's going to be grid.size. We'll just say edge case. If grid.empty or grid0.empty, or sanity check is really what it is. So rows is going to be grid.size, and then column is going to be grid0.size. Let me think for a second. So excuse me. Yeah, that's the number of rows. Yeah, the number of columns, right? Correct. Okay, good. Balance check is just going to be int I, int j, or just row column. It's probably better. It's easier to think about it if you just say rows and columns. Now we're going to have rows and rows. I like to do instead of n rows and columns. We'll do n rows and columns. We'll say return rows greater than 0 and columns greater than 0 and rows less than n rows and columns less than n columns. Okay. Balance check. There you go. So flood fill, we'll say base case if if not bounds check of row column, and return. Right, if you fail the bounds check, otherwise you're going to flood fill in 4 different directions. We can have standard, now this is going to be interesting, array of directions. We can do something like this. There's a way to do all 4 directions, right? Well, I like doing it this way. This is one approach. There are a few different ways to do it, but there's 0, 1. Oops. That's just kind of personal preference. 0, 1, 0, negative 1, 1, 0, and negative 1, 0. Or probably want to do it in like a clockwise direction, so you can do up is -1, 0. To the right is 0 plus 1. Down is +1, 0. And right, so this is rows and columns, right? So -1 row is up, add a column to the right is to the right, add a row is down, and subtract a column from the column right to the left would be to the left. Yeah. So we have directions here. So now we can actually even loop over the directions for auto D in. How do you do this? You do for all 4 auto D directions. You could even do, can you do this? You do dr, dx, dc. I wonder if you can do destructure like this. I don't know if you can. We could try it. And then we'll flood fill with, which is itself, really it's f of row plus dr, column plus dc, f. And the idea is we say, base case, say if so we have the bounds check, we'll say if grid of row column is equal to it's equal to 0. It's a character, right? So if we're equal to a 1, then we want to set grid row column to an X, we'll say. Otherwise, we want to return. If we, so if we see a 1, we're going to recurse, set it to an X and recurse. Don't recurse on anything that isn't a 1. Yeah, all right. So this is kind of a funky way to do this, but it works. I don't know if I can do this this part here, the initialization, we'll call it, or the, destructuring. Yeah, destructuring. I don't know if I can do the destructuring this way. I hope I can. That'd be nice, but it might not work inside the for loop like this. Sanity check, get the number of rows, number of columns. We have a bounds check. We get the directions, vertical, horizontal directions. Run our bounds check. If you're out of bounds, obviously don't do anything. Just return. So this is guaranteed to be in bounds. And then see if, don't recurse anything that isn't a 1. Set this to an X. And yeah, and then keep, right, so you can keep flooding. So you fit flood fill. We're just gonna do flood fill of flood fill of, we'll just do grid 0, 0. I just want to see if this will run, if this compiles. Array, too few. Oh, I need to do 4, I think. It might be the other way around. Declaration. Bounds check cannot be implicitly. I could, yeah. No matching function for call to object of type lambda. Row column O. Give this a shot. Non-void does not return. Okay. Okay, sweet, compiles. Nice. All right, interesting. So this destructuring seems to work. And then what you're gonna do is check each position and flood fill in the grid, increment by 1 when an island is found. It's found, and flood fill the island. Doesn't in tandem, so that the check doesn't count any island twice. This problem you also can use. So this is one way of doing it. There's another way that involves using an interesting data structure, which is called the, what is it called? It's got a name. Disjoint set. Yeah, disjoint set data structure. The disjoint set data structure is an interesting. Disjoint set data structure is also an interesting way to do this as well. So say if grid of row column is equal to 1, ret is going to be 0, plus ret, and flood fill row column with yeah, that's pretty much it. That should do the trick. Oh, no, really? Shucks. No. Uh-oh. Uh-oh. That's not good. That's not good. Oh, this actually works, this destructuring. That's awesome. Sweet. Wow. Okay. I'll remember that. That's cool. I like that. However, something went wrong. Something went wrong. You know, you could do this too. That's probably better. So you do a bounce check, and you say if it's a 1, then we'll set this to X and recurse. Huh. Wait a minute, really? 1, 2, 3, 4. This should, once it flood fills, we shouldn't increment ret again. Like that should be it. I'm missing something here. Something's not right. No. No. The flood fill should clear the whole island. Like that should be it. The flood fill. That should clear the whole thing. We could print the grid, I guess, after the flood fill, which looks like the same for loop. Call it R and C. Okay. All right. After the flood fill, what do we get? That's not right. Oh, come on, man. That's why. Well, but I've done this so many times. Make so many mistakes. Done it so many times. Great. Okay. Because I wasn't touching the row or the columns the first row of the first column because the bounds check didn't have an equal sign in there. That's silly. Come on, bud. Come on, bud. Can do better than that. So I'm pretty sure this works. We'll implement also. We'll go through the. The other question too. All right, let's go for it. Hey, we got there. Sweet. Yeah, so this is kind of a classic problem. Pretty straightforward solution. Obviously, this is if you're allowed to mutate the grid. Obviously, you could create a copy of the grid and mutate that grid. If you're not allowed to mutate the grid, that won't cost you any extra memory because... Oh, no. Yeah, I mean, if you're not allowed to mutate the grid, you could... yeah, if you're not allowed to mutate the grid, you could just create a copy of the grid and do the same thing. Although you would use more memory if you did that. This obviously didn't use any memory beyond this. This just destroyed the grid though. Replaced the islands with X's instead of 1s. Yeah, there's a disjoint data structure that you can use to do this as well, which I don't want to do. I don't even want to bother. The disjoint data set structure, I think, is, in my opinion, it's kind of challenging to find the actual use cases for, because I used to think this was a good use case for it, but actually this question can be done without it relatively easily. But this is kind of interesting, this data structure. I've gone through this a few times now. I kind of remember what to do, but basically this would like group the islands into their own sort of like, if you can imagine like a flattened tree, something like that, where each element of the island is another node in the tree, and then the tree gets smushed into like basically one node at the root, and all the other nodes are children of the root. It's kind of funky, but that's sort of what this data structure does, and it's an efficient way to kind of sort of determine these islands, I guess. Partitioning of a set. Track of the connected components of an undirected graph. This model can then be used to determine whether two vertices belong to the same component or whether an edge between them would result in a cycling unifying algorithm using high-performance implementations of unification. Solving equations between symbolic expressions. Okay, interesting. It's used by the Boost graph library to implement its incremental connected components functionality. Yeah. So that's the other thing too, is that determining whether or not components are connected, you don't even need to use this for that either. This data structure is really only useful if the data structure itself is changing over time, or if you're doing incrementally finagling with connected components. Like it kind of only makes sense. Like if you're partitioning a set that's changing over time, something like that. That's sort of what you would use something like this for. It really has a lot more to do with changes in the data that you're working with, rather more so than it does, in my opinion, like Kruskal's algorithm, I think, right? Minimum spanning tree algorithms. So apparently minimum spanning tree algorithms, it's useful because I guess you're kind of updating things incrementally. That's sort of why, I guess. Yeah, it's kind of a unique test use case for these things, because you can kind of get a workaround. You don't necessarily need to use this algorithm. So like this number of islands, right? Obviously this grid is sort of static, right? You're sort of just taking the grid as it is. But let's say let's say the grid was really like a graph, and things are being added to that graph over time. All right, then you wouldn't want to use this approach. You'd want to use a disjoint data set structure, so that way you can efficiently add pieces and keep track of them. like knowing how many components after a piece has been added, how many components you still have, as I guess edges and vertices are added to the graph. That would sort of be like why you would use a disjoint data set structure. And then obviously minimum spanning trees, that's sort of how the algorithm goes, I believe, is that you add vertices and respective edges and vertices to build the spanning tree sort of incrementally. So that would make sense. And you don't delete edges though, which is interesting. Although I think you could modify disjoint set forests, disjoint sets, data structures to actually delete edges if you wanted to, edges and vertices. You probably could. I think you probably just need a. Yeah, I think you could. Just say I think you could. And this partition refinement, dynamic connectivity. So these things are related. Yeah. Worst case behavior disjoint sense in the length of Davenport-Schinzel sequences combinatorial structure that computational geometry. Yeah, so these, I tried to figure out what these mean, what these are, and I couldn't understand it. I think I would have to like really study it to figure out what is a Davenport-Schinzel sequence. Like those are kind of hard to wrap your brain around in the first place, just like what the description itself of what that is. It's interesting that these worst case behavior of these sets is related to these sequences. That's definitely an unusual thing. But anyway, so yeah, this is an interesting question. You could use this approach. I prefer this approach. You could also use disjoint set data structure as well. But I wouldn't recommend that. I don't think that's really good. Typically, it's not really the best. All right. Okay. So that will be it for this question. I'm not going to go into too much more detail beyond this, I suppose. We can maybe look at solutions and discussion. I'm not going to bother. I've seen this question like numerous times now. Let me. Okay. So let me end the stream here. So that'll be this question. Thank you all for watching. Talk to you soon. Follow me on Twitter. I like posting stuff on Twitter, man. I don't know. I have a Twitter now, so I guess I should be plugging it. Yeah, take care.